So before we talk about the quiz, Monday's quiz, quiz 12, let's talk about the final exam. It's on May 4th. The download on like it happened at the midterm. So it goes live at 8 o'clock. You're supposed to upload it by 11:30. That's RIT time. There's 8 questions. Things that are not on the exam: no Eulers, no convolution, no proofs, variation of parameters, a Bernoulli question. There's no question where there's 2 tanks. But guaranteed on the exam, there is a tank question. Obviously, there's Laplace questions, and for sure there's a first order linear, a y prime plus py equals q question on there. So in order to sort of combine the ideas of a couple of these things, this is an old final exam question from a couple of years ago that has Laplace in it, and it's a tank question. You won't have Laplace on your tank question, but this is one year where I did combine them together on the final exam. And this will pertain to studying for the final and for Monday's quiz, because Monday's quiz is about solving differential equations with Laplace, and we have to first get into the Laplace world with Heaviside step function and get out of the Laplace world with Heaviside step function. So let's take a look at this question. Salt water is pouring into a full 20-liter tank at 2 liters per minute. The inflow initial concentration is 2 kilograms per liter, but after 30 minutes, the inflow concentration switches to 1 kilogram per liter. So the inflow is not a constant. There's a switch in there. I'm going to have to write the inflow concentration with the Heaviside step function. It's got to go 2 down to 1. Okay, finish the rest of the question. Brine in the tank is well mixed. We know what that means. That means that the outflow is the whole tank is homogeneously mixed. So the outflow is the same in the tank as the outflow concentration is the same as the whole tank concentration, and it drains out at a rate of 2 liters per minute. Okay, 2 liters per minute going in, 2 liters per minute going out. This one, the volume doesn't change. It's a constant volume of 20 liters. Okay. We call y the grams, I guess I mean kilograms, because we're doing everything in kilograms here, of salt in the tank time t. The tank is initially full of fresh water. Okay, so initially then y naught is equal to 0. Let's solve the differential equation. So when we're doing these tank questions, it's always y prime in kilograms per minute. Salt rate of change of salt in the tank per minute is always equal to in minus out. And the in, we get the in and the out the same way. Concentration, a concentration which would be in kilograms per liter multiplied by liters per minute. So kilograms per liter times liters per minute, the liters cancel out and you end up with kilograms per minute in minus kilograms per minute out. Now let's look at this in concentration, which would have the units of kilograms per liter. Initially it's 2, but after 30 minutes it drops down to 1. So I want to turn on the Heaviside step function at 30 minutes, and the function I want to turn on, I want to subtract 1. So you can either put the minus in or I left it out. So let's check this out if I'm correct. For times before 30 minutes, this u of t minus 30 is 0, so it's 2. So initial flow is 2. After 30 minutes, this u of t minus 30 is 1, so it's 2 minus 1, 1. So I've got the in concentration in kilograms per minute written with the Heaviside step function. So I got y prime equals, this in concentration then is this expression. Put that in brackets. And I want to multiply, so this is kilograms per liter. I want to multiply this by liters per minute. It's a constant 2 liters per minute. Out concentration, y kilograms divided by 20 liters, there's the out concentration in kilograms per liter times liters per minute. Here's my differential equation then. Let's let's simplify that. So I'm going to multiply the 2 through the brackets. That makes this a 4, and that makes this a 2. The 2 cancels with the 20, gives that a 10. And I'm going to bring this over to the other side so it looks more like the way that we were regularly doing it. And so I brought it over. This is the stage where we're at now. Now I'm ready to take the Laplace transform, which I've already done, but let's having that coffee. Let's talk our way through it. The Laplace of y prime is going to be SF minus y naught, but fresh water, y naught is equal to 0. So SF minus 0 is the Laplace of y prime. The Laplace of 1/10 y, 1/10 is a constant, so the Laplace of y, f. So here's the Laplace of the left-hand side. Now I'm taking the Laplace of the right-hand side. Laplace of 4, 4 over s. Now this is where we're taking the Laplace, we're going into the Laplace world, but with Heaviside step function. So Laplace of Heaviside step is going to be e to the minus as, minus 30s. Now let's look at our rule for getting into the Laplace. For going into the Laplace, we take our function that's turned on, that's switched on with the Heaviside step function. We take that function and we shift all the t's. Everywhere there's a t, we put a t plus a, I guess a t plus 30, and then we take the Laplace. Now, there are no t's, so we don't do anything. Now I just take the Laplace of 2. But if there was a t here, I would first, everywhere there was a t, put a t plus 30, the shift happens in time, and then take the Laplace. So now I'm in the Laplace world. I'm solving for f. I can factor out an f here and get this s plus a 10th. Now I'm dividing this bracket, this s plus 10 out, and I'm going to divide it on both sides. But I'm going to make it look easy for myself by when I divide both sides, I put it underneath each fraction. Here's now my function that I need to unlaplace. So I'm going to have to do partial fractions on this first piece. So let's break that up with partial fractions. I don't like the way that the machine writes it. I'm going to multiply top and bottom by a 10th. Because I like that s plus a number, because that's going to make it easier to unlaplace. Right? This is going to unlaplace to be 40 e to the minus a 10th. Okay. Plus, now, I have this piece here. Now I'm going to do partial fractions this also, but I mean, what's inside the square bracket is just half of what's outside the square bracket. So this will partial fractions. I can save myself the effort. Instead of a 40, it's just going to be a 20. So I can unlaplace each piece. So now that was just partial fractions. Now I'm set to unlaplace. Let's unlaplace the stuff that's outside the square bracket. This unlaplaces just like normal. So unlaplacing f to y, the inverse Laplace. Unlaplace a constant over s, that's 40. Minus 40 e to the minus a 10th t. So unlaplace. Now I'm that takes care of the stuff that's outside the square bracket, that's not affected by the Heaviside step. Now I'm going to unlaplace this piece. So the e to the minus 30s is going to unlaplace to be that Heaviside step function. Let's go back to our chart. Getting out of the Laplace world. the e to the minus as unlaplaces to be the Heaviside step function, the unit step function. F of s unlaplaces to be f of t. But everywhere there's a t, I want to put a t minus a. The argument inside the square bracket has to match the argument in the Heaviside step function. So first figure out what the inside the square bracket would normally unlaplace to be. So normally, the thing under in the square bracket, like if it wasn't times by the Heaviside step, would unlaplace to be 20 minus 20 e to the minus 1/10. T. That's what it would normally unlaplace to be. But I want the argument inside the square bracketed piece to exactly match the argument of my Heaviside step. So I got to be careful with the brackets. Everywhere there's a t, I put a t minus 30. That's using this rule to get out of Laplace. Okay, actually now I'm good. This is the solution to that differential equation. We could at least make sure it goes through the initial condition. If I put t equal to 0 in, well, Heaviside step at 0 is turned off because it's this Heaviside step is 0 before all times that are before 30. So that would be 0 times the square bracket. That whole thing wouldn't be there. So it would just be 40 minus 40, e to the 0 is 1, 40 minus 40, 0. Okay, it goes through the origin. At t equals 0, there's no salt in the tank. It's fresh water, so that works. So here I've got it written as a split function. Before 30, this u part is all 0, so this is all turned off. It's all blanked out. After 30, that u is 1. It's turned on. So after 30, that's what I have. If I put that minus sign through the bracket, that's going to flip this to be a plus. 40 minus 20 is going to be 20. And there's my expression. Now there's something else we can check, right? This is a piecewise function, but it's supposed to be a continuous piecewise function. Those pieces should line up at 30. If I put 30 into here, I get 40 minus 40 e to the minus 3. If I put 30 into here, the bottom one, e to the 30 is 1, so I get 20 plus 20. There's the 40 minus 40 e to the minus 3. So the pieces line up. That's another check. Let's get that bonus. The bonus was, where's the maximum amount of salt? Well, let's graph this, and I only want to see what it looks like. My instinct is that the maximum amount of salt should be right at the switch point. So I'm only looking for times here. I don't want to see, I want to start time at 0. Let's go to, let's say, 40 minutes. I don't want negative salt concentration. Okay, show me that. Oh, it goes way up. Okay, there's the switch that happens. This is the curve, but it's supposed to stop at 30. At 30, then, we switch curves, and now I'm supposed to be drawing this for t's after 30. So I'm adding this other function. So there's the other function. Let's go to, I don't know, 60. We'll go a full hour. So this is the function I'm following until the switch happens, and now this is the function I'm following. Yeah, so the maximum must happen at 30. So to answer, to get the bonus, all I got to do is put 30 into either one of these equations because we made sure that they lined up. So the answer would be for the bonus 40 minus 40 e to the minus 3. Okay, thinking about the quiz then. The quiz doesn't have a tank question on it, but the quiz, sort of the quiz format starts here, right? We could have given you, here's a differential equation with a step function, take the Laplace, solve for f, then on Laplace. That's the sort of thing that we need to do on the quiz using your chart. How does that sit with you?